He's talking about the cubic instability of the Q-tensor theory for nematics. Thank you.
Thank you very much. So I'd like to thank Peter and the other organizers for the kind invitation and the opportunity to speak here, as well as Newton Institute for facilitating all these. In an attempt to connect with John's talk, I would say that one of the messages that he tried to transmit was that it really makes a difference as to what kind of mathematical objects you use in order to describe the liquid crystals, because you can get very different predictions depending on what functions you use. And overall, you need to use some kind of functions to describe these configurations, right? So you have a domain and a target. And John mostly concentrated on what happens, what kind of variations, spatial variations you allow in the domain of these functions. But that's not the end of the story, because it also matters what kind of target you use. And there is a rich choice of possibilities, namely you can describe liquid crystals using these director theories. So you can use unit length vector fields. So this means that you attempt to describe at each point in the domain liquid crystals using 2 degrees of freedom in the target, right? So if you have a unit length vector field, that's 2 degrees of freedom. And that's quite a nuisance, this restriction to using only 2 degrees of freedom, because you have this Lagrange multiplier, and that actually causes also problems in the domain, in the spatial variations allowed, because as John pointed out, you have troubles with the energy becoming infinite if you have, say, line defects. One other thing that you could do is to use as a target space not only something that has 2 degrees of freedom, unit length, vector fields, but also a scalar or the parameter, and that's what Ericsson proposed, right, for nematics, uniaxial ones. And then you describe your liquid crystals using objects that at each point in the domain have 3 degrees of freedom, unit length vector field, and a scalar or the parameter. Or you could do even worse, or better, depending on how you look at things. Namely, you use these matrix valued functions, right? At each point in the domain, you have a matrix, right? Traceless 3x3 matrix. So that's overall 5 degrees of freedom. So you attempt to describe the same physical object by functions that at each point in the domain have either have in the target space either 2 degrees of freedom, or 3 degrees of freedom, or 5 degrees of freedom. And of course, you could be more ambitious and go on, try to use functions that take values into a higher dimensional target space. So then the question is, what is the right and optimal thing to do? Of course, if you use more complicated objects in order to describe the nematics at each point in space, you will have more comprehensive description, but you also have much more complicated equations. So you want to strike a balance between you know, how complicated your equations are and what you manage to capture using more complicated objects. So one of the things that I've been very passionate about in the last few years is to understand what do you gain if you use more complicated descriptions, right? If you use a Q-tensor description as opposed to a director description, right? So what are the things that can be described only using matrix valued functions and not vector valued functions? And overall, my feeling so far is that the matrix valued functions, the Q-tensor description is better when you attempt to describe small scales, localized structures, so defects, or when you attempt to understand what happens on a global level, at the topological level. But my talk won't be about the benefits of using Q-tensor valued description, but rather about the troubles that you get if you try to use these tensor valued descriptions. So this is so-called cubic instability. I'm sure this is not standard terminology, so I'll explain in a moment. It has to do with that L4 term that John mentioned earlier. So once you decide what kind of mathematical description you want to use, the simplest, what kind of functions, right? The simplest setting that, the simplest mathematical setting that provides you some kind of predictions has to do with energy minimization, right? So you can try to minimize an energy functional, something like that. Okay. So you integrate this kind of energy density where you have this matrix valued function Qij. Ij is 1 up to d. D is either 2 or 3. Well, the most physical one is really 3. And you have this d here, which is supposed to stand for gradient of Q, whatever that is, a third order tensor. And the minimal requirement that such an energy functional should satisfy are the physical invariances, namely the Galilean invariance and the material symmetry, which amounts to this kind of relation, namely psi of qd is equal to psi of q star d star, where q star is a rotation of q, and you have this relation between d star and d. And here you assume, of course, summation over repeated indices, and that is for any rotation. Now, you can organize things a bit and decompose this into something without gradients and the remainder. So you have the so-called bulk part, and then something that contains gradients and things without gradients, the elastic part. And for the bulk part, this physical requirement implies that you can write this psi, the bulk, as a function of the principal invariance trace of q squared. And here I should have put determinant of q, but you can easily check that for a traceless symmetric matrix, determinant of q is equal to trace of q cubed divided by 3. So you can do it like that. And as mentioned before, you have the good examples of elastic terms, so terms with derivatives that respect these physical invariances, namely this I1, I2, and I3. And then you have this trouble term, which is cubic, and that's what, well, that's what will cause the instability. So what do you have here? This comma k is derivative with respect to the xk variable, and you have summation over repeated indices. Okay, and you can also check that I2 minus I3 is a non-Lagrangian, because you can write it in this divergence form. Now, the good ones, I1, I2, and I3, are quadratic in the gradient. And this is also, well, you have here the square of a gradient for all practical purposes, but you also have this term that causes troubles, at least if this thing here that doesn't have any gradient is large enough, right? If it's not large enough, you can hope to use the good effect of the other three terms to control this trouble term. But I'll be more specific in a moment. So you have this elastic energy with 4 terms, 4 elastic constants, and now the question is whether or not you should use this L4 term. If you do it, well, you have a bit of a huge problem, namely this energy functional is unbounded from below, which you can see by taking, for instance, like John did it, an ansatz of this form, S of x times the tensor product of x over mod x minus 1/3 of the identity, and then you see that the I4 term reduces to something like this, and you can easily make this arbitrarily negative because here you have this destabilizing S in front of the term that is supposed to be good and control things. So if you take this as negative in particular, well, after a bit of work, you can make this energy functional unbounded from below. If you take this L4 to be non-zero, if you take L4 to be 0, then if you put the bulk part to be 0, you have this relation, right? So if you have just L1, L2, and L3 non-zero, you have that the energy is bounded from below by this gradient times a constant, and this only holds, of course, if you have a relationship between L1, L2, and L3. This is an if and only if situation. And you see, this thing here is good because that term, that cubic term, which was looking like a gradient square times q, can be hidden in here, right? If q is, morally speaking, smaller than this, whatever that means, because q is a matrix. But I'll get to this in a moment. And well, q is small enough if the eigenvalues are small enough. That's how you can think. And this is related to the other issue that John mentioned, this idea of physicality of Q-tensors. Namely, if you remember the statistical mechanics interpretation of the Q-tensor as the second order moment of the probability distribution function, so you have this definition, right, of the Q-tensor. You obtain a 3×3 symmetric and traceless matrix, but not any 3×3 symmetric and traceless matrix can be written in this form, because if you have a form like this, then you also have some restrictions on Q. More precisely, you see that the eigenvalues of Q are bounded between minus 1/3 and 2/3, and that's pretty easy. If you note, if you take eigenvectors of Q and apply to this thing here, you obtain this quantity, which should be at most 1. So it's a positive thing between 0 and 1. And if you just integrate this thing, you should get 1. So overall, it's easy to check that for physical Q-tensors, Q-tensors that are obtained like this, the eigenvalues should be bounded between minus 1/3 and 2/3. Okay, so morally speaking, if you have a physical Q-tensor, you can hope to use the smallness of Q to hide this cubic instability into the good part of the elastic energy, yeah, and have no instability whatsoever. Now, going back to what I started with, namely other theories, you can see that you can embed the other theories into this larger one, the Q-tensor one. And you have these names for Q-tensors that you heard again and again, namely isotropic if Q is 0, uniaxial if it has 2 eigenvalues, and biaxial otherwise. And Erikson's theory can be seen as a restricted version of this Q-tensor theory, in which you take only uniaxial, in this sense, Q-tensors, so only Q-tensors that have 2 equal eigenvalues, and then you can check that you have a representation like this. So Ericsson actually worked with things like this, not with matrices. And then if you take S to be a constant, you get the Ozin-Frank theory, right? So you can embed all the other theories into this one. But what's the relation between the theories? Well, you can check that if you take Q of X to be of this form, where S is now a fixed positive constant, so really this is a matrix that depends only on these unit length vectors, and you take these relationships between the L constants that appeared before. Remember that the energy was sum of Li, I, well, Lj, Ij. You get this relation between the Q-tensor theory and the theory that works very well, the Ozin-Frank theory. But this gets me back to the L4. You only get this reduction of the Q-tensor theory to Ozin-Frank if you have an L4 here, right? Otherwise, you won't be able to get the Ozin-Frank energy out of the Q-tensor energy, right? So that's why you need L4 to recover Ozin-Frank, okay? So you have now two issues. You need L4 in order to recover Ozin-Frank, but on the other hand, L4 comes with troubles, namely you get things unbounded from below. The energy is unbounded from below if you put L4. So one way of dealing with the instability created by L4 is to say that if you require in addition that you work with physical Q-tensors, so bounded Q-tensors, bounded eigenvalues between -1/3 and 2/3, then you can hide the part that creates the L4 instability into the good part with L1, L2, and L3. But the trouble is that it's not clear in general how to connect the physicality, so the requirement that Q is bounded with the energy functional. And one way of doing this is to use this singular bulk potential that John mentioned before. So you put in the energy functional a bulk part which becomes infinite if the Q-tensor goes outside of the physical range. So if the eigen values are too large. And that's definitely a medicine that works, but I'm a bit suspicious sometimes about taking medicines because they have this bad habit. You can take something for the heart that affects the liver, and the other way around. So it's not clear to me what this singular potential brings. New, right, in the physical predictions of the energy function. It's a good thing. I used it myself, but I was wondering what can you do if you don't want to use this singular potential, but nevertheless keep the L4 term and work with a regular potential, the most common one, which is like A trace of Q squared minus B trace of Q to the third. Okay, so yeah.
I'm confused. So in Onsager theory, if you try to derive use Onsager theory to derive a nematic free energy, then you have this diverging potential. The potential it blows up when the rods, there's an entropy term that actually diverges, right? Or its derivative diverges.
Right, but that's a different theory, right?
Well, then the argument for expanding in powers of Q is saying near the transition I can expand in powers of Q. But of course the free energy really does have this sick tail. So
yeah, so near the transition point you have that this singular potential can behave like this expansion, Taylor expansion. That's what you're saying, right?
Right, so you're just saying physically I do expect to have this hard wall, right?
Okay.
Is that?
Yeah, and not only Onsager theory, and Meyer-Zalpa theory as well, or I think any kind of physical theory.
Right.
The entropic part of the free energy must diverge when the order parameter reaches its saturated value.
Or it's singular, it doesn't diverge, actually. It's derivative, the force
Okay,
derivative.
okay. Yeah, so that's what went into this other theory that John Ball mentioned in the previous talk, and Tim Slukin worked on this also a long time ago. So yes, that is part of the physical description.
Okay, okay. But coming back to my question is, if you are, for some reason, don't want to use a singular potential, the question is what can you do somehow, nevertheless, in order to still get some consistent understanding. And what you can do, if you are more philosophically minded, is to remember this thing, which says Panta Rei, which is attributed to Heraclitus. Namely, you can say that if an energy minimization doesn't work, maybe you should look into a dynamical theory and ask yourself, if you start with an initial data which is finite energy and also physical, would the gradient flow of this energy preserve this physicality? Namely, both the physicality of the Q-tensor and keep the energy bounded. And what I'm saying here is to consider the gradient flow generated by the energy. Well, the question is then, what is the gradient there? There are several possibilities actually to create a dynamical theory that has the property that the energy decreases along the flow, and this is just one possibility. So you can take this so-called L2 gradient. This is just the variational derivative, and you also have to put here some lambda and mu in order to keep the constraint lambda is a Lagrange multiplier corresponding to tracelessness, and these mu ij correspond to the symmetry constraint for Q. So you get for this standard non-singular potential this kind of equation. And then the question that I asked is, if you start with an energy in which you use this regular potential and the initial data is physical, is this preserved by the flow? And well, the overall answer seems to be that if the initial data is small enough, then this is true, but if not, then you have troubles. You reach the similar situation that John had, namely things blow up. So what happens here? If you recall this abstract equation and you multiply with the right-hand side, okay, you get that the energy f of q decreases along this flow. So this tells you that this energy is a priori bounded. So you have this. Okay, but what is this actually buying you? Because you have this trouble term here, and if this is small, you can hope to hide this term into this mu. So if the eigenvalues are times the L4 are small enough, you can hope to hide this into this part and get a bound overall for the gradient. So things are well behaved. Because, this part, the regular potential doesn't cause you any trouble. You can control things. But the real question is, if this is initially physical, so small enough, does it stay like that? Well, and now I get to the question as to what is small enough. You can have this, what John called L infinity, which otherwise means this thing. So if you look at the trace of q squared, is bounded at any point in time and space. So the question is, if this happens initially, will you have this preserved for later times? That's what you need in order to make that L4 term harmless, namely controlled by the others. But on the other hand, this is not quite the same as the physicality. In the physicality requirement, you ask that the eigenvalues are between -1/3 and 2/3. So you see, if you have this requirement, then you do have this bound, namely the trace of q squared is less than 2/3, but not the other way around. So if you have this bound, you don't necessarily have that. These eigenvectors are between -1/3 and 2/3. And that's so. This physicality requirement is a bit more subtle than this brutal requirement here. And one thing that one should note is that this means that Q are actually in a convex set. Yeah. So the physicality, sorry, implies an L infinity bound, but not the other way around. Okay. So what you can do is to see that if you take an ansatz, which is again a radial hedgehog like this, you have instead of that gradient flow, this kind of one-dimensional PDE. And because of this L4 term, if the initial data is large enough, in a sense, then you'll have blow up in finite time for the equation. So this can be done by multiplying the equation by this quantity, you integrate, and you play a bit with things and obtain a blow up inequality for this quantity. So if, on the other hand, you have a small initial data, so that requirement that Q naught in L infinity is small enough, then this is preserved by the flow if you have this requirement. And that's probably just a technical issue, but at the moment we cannot get rid of it. So you can try to do something more complicated, in principle, namely to obtain a physicality preservation. So you ask yourself, if the initial data is physical, namely the eigenvalues are between -1/3 and 2/3, will this be preserved by the flow with a regular potential? And it turns out that this is true, and there is an intuitive way of understanding if the equation preserves physicality. And this has to do with a numerical analysis technique. Namely, if you have a general equation like this, so the time derivative of u is au plus bu, you can try to solve first the equation by setting b is equal to 0. And you obtain some flow, where here I denote the solution of the equation at time t, starting from initial data u naught. On the other hand, you could also do the same trick, but now ignoring a, right? So if I have just the equation dtu is equal to bu, you get another flow. btu is equal to, this btu naught is the solution of the equation of time t, and starting from initial data u naught. Okay? And then you obtain a solution for this thing by just taking, by first solving the equation, just taking a is equal to 0, taking then b is equal to 0, and so on. Yeah. So this is referred to as operator splitting, or fractional time step, or something like this in the numerical analysis world, and it's called nonlinear Trotter product formula in the more analytic world. But nevertheless, the point is that you can try to understand this equation as a successive, using successively either this operator or this operator. And then, if you consider just the simplest case, when say you have just L1, right? So you have just a diffusion equation. What happens here, and you do it in the whole space, make things even simpler, you have this formula for the solution of the heat equation starting from initial data F. Yeah, so you have this formula. And I put in blue these parts because I can rewrite this formula something like this. And now I denoted these blue parts with this mu. Okay? And the point for doing this is that these blue parts, if I were to take f is equal to 1, integrate to 1. So really what I have here is like a continuous probability measure, right? Because if I put here 1 instead of f, I get this integral is actually equal to 1. Yeah. And this is helpful because if I have this thing, which is a different way of writing the solution of the heat equation, I can approximate it with these simpler objects. In a technical sounding language, you have that I can write a probability measure as the weak star limit of convex combinations of delta measures, whatever that means. But one way of reading this formula is that I can write this integral as limit of convex combinations of Q naught of y. Okay, so this tells me in the end that the solution of the heat equation is, I mean, this is a tensor, is at each time in the closed convex hull of the initial data, right? So this means that, at least in this very specific situation, if I start with a certain convex domain in which the initial data takes values, that will be preserved. So the physicality is preserved by the heat flow. Okay, and then you can look at the other part, the regular potential, and this is just an ODE, and you can diagonalize everything, and also easily see that physicality is preserved because you can express things in terms of eigenvalues of Q. And then using that operator splitting idea, you can see that physicality is preserved, of course, in this simple setting. So what is overall the moral of this story? If you for some reason, you want to use a regular potential, you can try to do a dynamic theory, namely to consider a gradient flow. And then you see that this physicality preservation, namely you start with initial data that has eigenvalues between -1/3 and 2/3, and you want to see if this is preserved by the flow. And it turns out that this is related to the flow, to the energy being bounded. And you can see physicality as being a more subtle version of this maximal principle that I referred before, namely that L infinity thing. And again, the physicality preservation is related to having the energy bounded. So, yeah.
Thank you very much for an interesting talk. Can we have questions? Yes, Monsieur.
Yeah, I have a very naive question about these problems created by the L4 term. because actually the mathematical expression for the energy which we're using doesn't follow from any first principles, right? Because
Right.
it's always understood as a first few terms of some expansion. And then, of course, there is at least assumption there that it should be small, that Q should be small. If Q is not small, this whole series may still converge, right? But its properties may be different from those of the first few terms, which we inevitably use. So then the question is, does this automatically mean that there is a much stronger restriction, actually, on the eigenvalues of Q than the one which follows from its microscopic definition, not just from -1/3, it just might be small. Or in other words, that we cannot, it seems that we cannot separate this assumption from the very form of the energy which we're using. So what do you think about that?
Well, that's quite a physical question overall. So let me tell you, in some sense, my hope was also related to the K13 problem, right? There you don't have like singular potentials that would cure anything, right? So you can ask yourself if the gradient flow is well behaved, even though the energy is not well behaved. But that's a much harder question, so I tried something simpler, hopefully first. Coming back to your question, it's really a very complicated question as to what you consider, what you put in the energy, right? My point was what kind of theory can, if a statical theory fails, maybe a dynamical one can do better. If you try to use, in some sense, a minimal amount of requirements.
So in many physical systems, you also have another energy term which tries to increase a scalar order parameter. So electric fields, for instance, would actually be trying to increase an order parameter once they're aligned, once the vectors are aligned and things like that. So there you've got another term which is worrying. It's trying to increase the eigenvalues above the physical bound. So can you put on bounds to, say, an applied voltage, for instance, that would then say, as long as my initial data is below some certain value for the eigenvalues, I'm okay. Can you do that with this theory?
So you mean in the presence of this potential that has the effect of increasing?
Yeah.
I would say, I think the answer would be no in general, but I'm not sure what the specifics are. But I think then you have that even the energies can increase, right? No? Yeah, I'm not really sure.
John, you have a question?
Are you sure that this couldn't be done on the basis of the static theory by looking at paths down which the energy decreases?
What do you mean?
Well, because I mean, you're saying you start with certain initial data with, say, eigenvalues in the good place, and the dynamics won't take you to eigenvalues where they're in the bad place. But if it was the case that there was no path down which the energy was decreasing that connected such things, then it wouldn't really be a true dynamical effect. It would be something that just used the fact that the energy was a Lyapunov function.
Sorry, that the energy
Was a Lyapunov function.
So why do you say it's not a dynamical effect?
Well, I mean, it's not. I mean, there's more subtle dynamics which sort of which show you get surprising things which do not just follow from the fact that the energy is decreasing. But in some sense, the connection of dynamics with the calculus of variations is in terms of paths down which the energy decreases. So it could be that you're just using, or you just need to use that property in what you're doing.
So I mean, this is very strongly depend. I mean, at least the proof strongly depends on what you use as gradient, right? So at least this proof strongly depends on the paths, if you want to put it. But it might not be that it's necessary.
We are slowly running out of time. There's one last question that's been waiting in the back row.
You're passing to the gradient flow. So if you have a vector theory, every equivariant flow will be the gradient. But if you have a matrix theory, this is not always true. Does it pose any problem?
Sorry, what is not true? That any gradient flow?
If you have something which is covariant under the 5 representation of SO3, this is not necessarily a gradient. If you have something of order 5, for example, which you need in your theory.
So I just want some dynamical theory so that the energy is decreased, right? I mean, that's a possibility. It's not the only possibility. And at least for that choice of a dynamical theory, you have this preservation of physicality. But it might not be true in general.
But perhaps we should continue this at coffee, which is after the next talk. And so thank you very much.